Welcome to qnawire.
Hi everyone, so what we have is a bottle of R134A that has a volume of 0.0015 cubic meters. The initial mass is a saturated mixture that is equivalent to 0.55 kg, and this mass is at 26 degrees Celsius. The valve of the bottle opens so that the vapor escapes, such that the delta T is 0, so the temperature does not change, and our final mass is determined to be 0.15 kilograms. What we're asked to solve for is the heat transfer that's required to maintain the same temperature and pressure. So first, what we're going to do is write down our assumptions. We know that this is not a steady state problem because conditions are changing over time, and we can also assume that any changes in kinetic energy, any changes in potential energy, and any work are negligible and are equal to 0. Next, what we do is define our system as this bottle, and we can go ahead and do a mass balance and say that the mass coming in minus the mass leaving is equal to the total change in mass of the system. We know that there's no mass that's coming in, all we have is mass that's leaving, so this will be equal to negative ME is equal to M2 minus M1. Therefore, the mass that exits is equal to the initial mass minus the final mass. Next, we can do an energy balance and say that the energy coming in minus the energy leaving is equal to the total change in energy of the system. We can say this as the heat coming into the system minus the enthalpy that leaves is equal to the total change in energy, internal energy of the system, which will be M2U2 minus M1U1. Now we can go ahead and just isolate Qin and say that Qin is equal to M2U2 minus M1U1 plus MEHE. We can actually combine this energy balance with our mass balance and plug in for ME and say that Qin is equal to M2U2 minus M1U1 plus M1 minus M2 times the exiting enthalpy. Next, what we can do is go ahead and find the specific volume at the initial state. We can say that specific volume is equal to the total volume all over the initial mass, and this gives us as total specific volume in the beginning as 0.002727 cubic meters per kilogram. Next, what we can do is use the specific volume and with our initial temperature equal to 26 degrees C, this defines our initial state, and we can get our quality and our initial internal energy. So by using these two pieces of information, we can determine that our quality will be equal to 0.06499, and our initial specific internal energy will be equal to 97.45 kilojoules per kilogram. Next, what we can do is calculate the enthalpy of our saturated vapor refrigerant that is leaving the bottle. So since we know that this is a saturated mixture, we can just say that the exiting enthalpy will be equal to Hg at 26 degrees C. And looking this up in the thermodynamic table, we see that this is equal to 264.73 kilojoules per kilogram. We can then calculate the specific volume at the final state and say that V2 is equal to total volume over the final mass, and this gives us a total specific volume at the final state of 0.01 cubic meters per kilogram. Now combining this information with our final state temperature, which is equal to 26 degrees C, these two pieces of information give us that the final quality is equal to 0.3143, and our final specific internal energy is equal to 136.56 kilojoules per kilogram. Now we can use the information regarding the internal energies that we calculated to plug back into our energy balance equation. Recall that our energy balance equation for Qin is equal to M2U2 minus M1U1 plus M1 minus M2 times HE. So we have all of these quantities. We can go ahead and plug them in, and we get a final Qin that's equal to 72.8 kilojoules. And this is the heat transfer that's required to maintain constant pressure and constant temperature during this process.